So dear students, we are going to develop a video lecture series on metric topology, and in this video lecture series we are going to discuss right from basics all the concepts that are expected at any undergraduate course in metric topology. We are going to start with simple ideas in functions, different types of the functions, how to check whether a given function is 1, 1, on 2, and then different ways of proving the results, because in metric topology in future many results we are going to prove, and there are different mathematical techniques to prove these results. So also we will deal with different techniques of proving mathematical results. So to cover all the metric topology, we will start with simple concepts. The planning of this lecture series will be somehow like this. First we will study metric spaces. In this part we will study definition of the metric space and various examples of metric space. So this will be the first part. In second part we will study actually the concepts of open sets, closed sets, then limit points, interior point, etc. Then also in this course we will be studying complete metric space. Then next thing will be continuous functions in metric space, which we will abbreviate as MS metric space. Then also we will discuss connectedness, and finally we will also study what is compactness. So in general we will discuss all these 6 chapters prominently, and also with this, along with this, there will be many results that we will be discussing. But all this study will be done about metric spaces only. So in short, I can say that this is a video lecture series for the metric topology. So whenever I study metric spaces, whenever I am going to study continuous functions, in that whenever I study complete metric space, I need the knowledge of sequences. So sequence is also a function. Whenever I am studying continuous function, again I am dealing with functions. So it is a very high time to learn basic ideas of the functions. So whenever you know function is a relation, in 11th and 12th standards you have studied all these basic ideas, but in 5 minutes we will revise what is function. You know, function is a relation between the two sets, say A and B, where every element of A, this is very important, every element of A is associated with unique element of B. So you know that there are types of the relations. Whenever I study the chapter relations, we have studied what are the different types of relations. Anyone remembers? It is 1-1 relation, then it is 1-many relation, then there is concept called many-one relations, and there is many-many relation. So these are various types of the relations. Always whenever I say relation, I am relating two sets, elements of one set are related with elements of other set. So whenever I say there is a relation between A and B, then what happens is elements of A are related with elements of B by some formula. Means suppose I take a simple example. Suppose I take A as the set. Say it contains the elements 1, 2, 3, 4, 5. This is suppose the set A. And B is another set, and suppose it contains the elements 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These 10 elements B contains. Now I define a relation between A and B. That means what? I am going to associate every or some elements of A with elements of B. Now suppose I define a relation in these two sets by saying that X or Y, if and only if X is less than or equal to Y. Suppose I take this relation. Now whenever this is a relation from A to B, this X is from A and Y is from B. Now if I define this relation, X is less than or equal to Y, then what? This relation 1 and 1 will be related because 1 is less than or equal to 1. 1 and 2 are related because 1 is less than 2. 1 and 3 is related. In short, 1 is related with all the elements because 1 is less than or equal to 1, less than 2, less than 3, etc., less than 10. What about 2? 2 is related with 2 because 2 and 2 are equal. 2 is not related with 1 because 2 is not less than or equal to 1. But 2 is related with 3, 2 is related with 4, 2 is related with 5. So in this particular relation, one element of this set is related with more than one elements of this set. Such a relation is called as a one-many relation. Okay. So what is a function? See, these are different types of the relations, but which of these types of relations can be functions? Anyone has any idea? Simple answer is only those relations where every element of this set A is related with unique element of the set B, then that relation is called as a function. Whenever I say it is relation from A to B, A is called domain of that relation and B is called codomain of that relation. But here I am talking about function. So function is that relation in which every element of domain, that means here in this case A, is related with unique element of the set B. Then that relation will be called as a function. See, for example, we can quote another example. Suppose I take set A as the set of elements 1, 2 and 3, and suppose I take set B as 1, 2, 3, etc. up to 10. And then we will define a relation between A and B as X or Y if and only if Y is equal to X square. So this is the relation, this is the formula by which element of this set A will be related to this set. So what will happen? See here the definition of the relation is Y is equal to X square and X is from A. So X can take values 1, 2 and 3 because this X comes from A. Now Y is equal to X square. So naturally you can see that 1 is related with 1, 2 is related with 4 because 2 square is 4, 3 is related with 9. So this is 3 square is 9. So in this particular relation you can easily see that every element of set A is related with unique element of set B. 1 is not related with anything other than 1. 2 is related with only 4, not related with any other elements other than 4 of the set B. So this relation will be a function because function is that relation where every element of domain is related with unique element of codomain, and so this relation is a function. So in short, which types of relations out of these 4 can be functions? Simple answer is one relation can be a function and many one relations can be a function. So this is basic theory. Functions emerge from relations. So we should have this basic understanding that any relation in which every element of the domain is related with unique element of codomain as it happens here, then that relation becomes a function. Now whenever I say functions, in general it is denoted like this: f is a function from a to b, and it is pronounced as f is a function from a to b. Now when f is a function from a to b, a is called what? Domain of the function, and b is called codomain of the function. So domain is the set of the elements on which we operate the function. So I will operate the function on the elements of a, and whenever I operate the function on the elements of a, whatever I get is called as the image of that element, and it is also called as a functional value, and functional value belongs to the set B. In this example itself, again if I repeat, here this definition can be converted as a function. So here my set A is 1 to 3, set B is 1 to 10, and I define a function f from a to b by this formula: f of x is equal to x square, where for all x belonging to a. Suppose I define this as a function, then we can easily see that a contains the three elements 1 to 3. So you can calculate f of 1, it is 1 square, so it is 1. Then f of 2, it is 2 square, so it is 4. Then f of 3, which is 3 square, so it is 9. So what are the set of functional values? 1, 4 and 9. Right? This is the set of functional values. This is called what? Range of the function. This is range of the function. So range of the function is set of functional values. Right? So whenever I say function is defined from a to b, all of you must know that this is called domain of the function. This is called codomain of the function, and this is called range of the function. So range is set of functional values. It may happen, now in this particular case what has happened is range of the function, which is 1, 4, 9 only, it is subset of B, because B contains elements from 1 to 10. B is superset of this range of this particular function. So in this case what has happened is range of f is subset of codomain of the function f, and this is a proper subset. Such function where range is proper subset of codomain is called into function. This is into function. All these things you have already studied in junior college mathematics, but still we will revise it. So range is subset of codomain, proper subset of codomain, then it is into function. Now when range is equal to codomain, it may happen that range of the function equals codomain of the function. In this case, the function is called onto function. We can use same example. Instead of b as 1, 2, 3 up to 10, suppose I take in same example, you will take a as say 1, 2, 3, and if I take b as say 1, 4 and 9, and if I define a function f from a to b by f of x is equal to x square for all x belonging to a, what now you will see? F of 1 is 1 square, so it is 1. F of 2, 2 square, it is 4. F of 3, 3 square, which is 9. So here range and codomain will be equal. And so this function is onto function. This is not into function. Into function means range is proper subset of codomain. Here range is equal to codomain. So this is onto function. Right? So any time, any function you take, what is the relation between range and codomain? Range is proper subset of codomain. It will never happen that codomain is subset of range. Range is superset of codomain. Never it will happen. At most what can happen is range and codomain are equal. And in that case function is onto. This is function is into function. Range is proper subset of codomain, and when range and codomain are equal, then it is onto function. So is it clear now what is into function and what is onto function? What you have to do is just calculate range of the function. What is range of the function? Set of functional values. When you calculate set of functional values, you will get range of that function. Compare it with codomain. If it happens that range and codomain are equal, onto function. Range is proper subset of codomain into function. So very simple idea. One small example or exercise I will give for you. Try to answer that. Suppose I define a function, a real valued function defined on set of real numbers. Suppose I define a function like this. F is a function from R to R. And our definition is, suppose f of x is equal to x square for all x belonging to R. Now what will happen here? You take any real number. This is my domain. So I am taking x from R. Output will be x square. So that real number that I take may be positive, negative or 0. But the square of every real number we know always it is non-negative. So in this case what will happen? Range of the function Rf, suppose in short I take, range of the function is equal to, in this case, what it will be? R plus union singleton 0. Where what is R plus? R plus is set of positive real numbers. So here R plus union 0. So in this case, range of this function will not contain any negative real number. Positive real numbers or 0 is the range of this function. And so here easily you can see that range of the function Rf is proper subset of codomain of the function. Because codomain of the function is R here, which is R. So range is proper subset of codomain, and so this function is, here in this function is, f is into function. F is into function. Range is proper subset of codomain. So this is how you can check whether function is into or onto. Now there is another thing about functions. We are always saying function is 1 1. So when function is said to be 1 1, what is the idea behind saying function is 1 1? Very simple. In functions what happens is you are associating to every element of domain unique element of codomain. Now when the word itself makes the idea clear that when function will be 1 1, if I take distinct elements of domain, distinct elements in domain have distinct images. Distinct elements in domain have distinct images. See, this terminology you must always remember, that whenever I am taking, whenever I am saying in general you say y is equal to f of x. So x is the element of the domain because I am operating function on that, and y is the outcome of that function, or it is called as the functional value. Now terminology says that this is image, this is image, y is image, and x is what? Pre-image. Y is image and x is pre-image. So whenever in case of this function, what you will say, f of 2 is 4 because 2 square is 4. So 4 will be called image, 2 is called as a pre-image. So if I take different pre-images, their images must be different, then the function will be 1 1. Distinct elements in domain have distinct images, then this function is called as a 1 1. Is this function 1 1? Whenever I define R to R function, fx is equal to x square, this is not 1 1, because you can easily see that 2 goes to 4, also minus 2 goes to 4, 2 goes to 4, and also minus 2 goes to 4. So two distinct elements, but their images are same, because 2 square is 4, minus 2 square is also 4. So this is many one function. This is not 1 1 function. Many in mathematics means more than 1. So here what has happened is two distinct elements have same image. What I am saying here, distinct elements in domain have distinct images. So this f of x is equal to x square is not a 1 1 function. Why? Because two distinct elements, 2 and minus 2 are distinct, but their image is 4, which is only one element. So this is many one function. Can we give an example of a 1 1 function? Many examples can be taken. For example, suppose I take f is a function again from R to R, and if I define a function as say f of x is equal to 2x plus 3 for all x belonging to R. Can we prove this function is 1 1? What is the method for doing that? You take distinct elements of domain, prove that their images are distinct. But instead of doing that, means what I have to prove? Actually what I have to prove, if x is not equal to y, implies fx is not equal to fy. I want to prove this when I want to prove function is 1 1. Because distinct elements in domain, these are the elements in domain, distinct means they are not equal. So x is not equal to y, I want to prove that their images are distinct. So this is an implication, if then statement. If this happens, then this happens. In 12th standard you have studied in logic chapter that contrapositive statement of implication and original statement, they are logically equivalent. So what is the contrapositive of this? Contrapositive statement will be if fx is equal to fy, it implies x is equal to y. So generally this method is used to prove that function is 1 1. So what is done is, if you start with fx is equal to fy, so you assume that x and y are elements in the domain where fx is equal to fy and conclude that x is equal to y. See how we will do this particular thing in case of this example. We have f a function from R to R. Definition is f of x is equal to 2x plus 3 for all x belonging to R. I want to prove this function is 1 1. I want to check, we will say, whether this function is 1 1. So what I will do is, we will start with two elements. We will start with fx is equal to fy. So we will say let x and y belonging to domain R be such that fx is equal to fy. Now when you say fx is equal to fy, it means 2x plus 3 is equal to 2y plus 3. Now I can remove 3, that means subtract 3 from both sides, and I can get 2x is equal to 2y. Then dividing by 2, I will get x is equal to y. So it means what? I started with fx is equal to fy and I proved x is equal to y. This implies what? F is 1 1. This is also written in this way, f is 1 1 function. Okay, so now I have told you what is meant by into function, what is meant by onto function, what is meant by 1 1 function. Again, in short, we will say when range is proper subset of codomain, it is into function. When range and codomain are equal, it is onto function. And when distinct elements in domain have distinct images, then it is 1 1 function. Okay, now is this function onto function? This I have to check. This is 1 1 function is okay. Whenever I define a function from R to R and I have proved here that f is a 1 1 function. Is it onto function? How to prove function is onto or not? Because you know what is meant by onto function? Range of the function. In case of onto function, what we have said, range of the function Rf is equal to codomain of the function. What is this in short? You take any element in the codomain, it is image of certain element in the domain. So if I want to prove that function is onto, R to R function suppose is onto, what I have to do is take any element of codomain, that means any real number you take, and you prove that there is some real number, because here domain is also set of real numbers. That image of that element is this element that you have taken from codomain. So in this particular case, what we will do is let y belongs to R. Y belongs to R. So you take any real number. y belonging to R. Now my responsibility is there is some element in the domain. Domain is again R. So there is some real number whose image if I take it becomes y. So how it is done? Very simple. Here in general you know fx is equal to 2x plus 3. This fx you take as y. So you can make this rough calculation. You can take y as 2x plus 3. So here y is expressed in terms of x. What you do is x you replace in terms of represent in terms of y. So this means what? 2x is equal to y minus 3 and x is equal to y minus 3 upon 2. Now as y belongs to R, this x which is y minus 3 upon 2, this also belongs to R. Because y is a real number, y minus 3 is also real number, and any real number divided by 2 is also a real number. So x which is y minus 2 upon 3, it belongs to R. And now if I consider f of x, what is the definition of f of x? 2x plus 3. So I will calculate f of, that is f of x is equal to 2x plus 3, and in this x you will replace x by y minus 3 upon 2. So it means 2 into y minus 3 upon 2 plus 3 I have to calculate. So this 2 gets cancelled, y minus 3 plus 3 is y. So you have found a real number. So there exists a real number. What is that real number? Y minus 3 upon 2 such that f of y minus 3 upon 2 is y. So what you have done here is, for every real number y belonging to R, you have found another real number y minus 3 upon 2 which also belongs to R, such that f of y minus 3 upon 2 is y. And this means every element of codomain is image of some element in the domain, and that is why this function is onto function. So this is how you can check whether functions are 1-1, whether function is onto, etc. What is the, in short, what is the method? If I want to show that function is 1-1, you start with x and y belonging to domain such that fx is equal to fy, prove that x is equal to y. It means function is 1-1. To prove that function is onto, what you have to do is start with any element of codomain. Now here, as it was R to R function, R is codomain, so we started with y belongs to R. Every time it is not y belonging to R, we have to remember y belongs to codomain. And then you prove that there exists some element x belonging to the domain whose image is y. It means every element of codomain is image of certain element in the domain, and that is why the function is onto. And when function is 1-1 and onto, when any function whenever I am given, and if I check whether it is 1-1 and I found that f is 1-1 and onto, then this function f is called bijective function. Bijective function plays very important role, because when function is 1-1 and onto, so if f is bijective function, then f inverse exists. So inverse of the function exists whenever original function is 1-1 and onto. That means if original function has these two properties, 1-1 and onto, then the inverse of the function exists. And we should know that when f is a function from a to b, its inverse function is from b to a. Right? So codomain, or also which is range, because this is 1-1 onto function, range of the function becomes codomain, because range and codomain are equal when function is 1-1 and onto. But whenever I consider inverse, range of f becomes domain of f inverse, and domain of f becomes range of f inverse. So this is the relation. Whenever original function is from a to b, its inverse function is from b to a. This is the relation between f and f inverse. So again, come to this same example. You already know that this function which is defined from R to R, by which definition? F of x is equal to 2x plus 3. You know this function is 1-1 and onto, and so this is f is bijective, and as it is bijective, f inverse exists. What is f inverse here? You can easily see we have developed here y. When I write y in terms of x, and if I manipulate x in terms of y, I get like this. So inverse function, see, in original function y is expressed in terms of x. By this rule, y is equal to 2x plus 3. So in inverse function, naturally I have to express x in terms of y. So what is x in terms of y? X is equal to y minus 3 upon 2. So here I can define f inverse x as x minus 3 upon 2. Y you can replace by x for all x belonging to R. So this is the inverse function of this function. Now when it is inverse function, you know that if I start with function f, I operate, suppose a is the element of, x is the element of a, f of x will be from b, and if I operate inverse, I will operate the inverse function on fx, I again will get x. So you know the rule, f of f inverse x is nothing but x, or if I take f inverse of fx, I get x. You can verify these results here. So this is a simple ideas: 1-1 function, onto function, into function, inverse function. When inverse function exists, all these are the basic ideas of the theory of functions. Right? Now there are various types of the function. There is something called zero function, constant function, identity function, etc. Quadratic functions, cubic functions, polynomial functions, logarithmic functions, trigonometric functions, exponential functions. These are various different types of the functions that we generally come across. So in short, we will take review of what are the different types of the functions, and in general we will study R to R functions, so that our domain will be R and codomain also will be the set of real numbers. So I need not always say f is a function from R to R. We will, for all this discussion about the types of the functions, we will take R to R functions. R to R functions means what? It is a function like this. F is a function from R to R. So domain is set of real numbers, codomain is also set of real numbers. Now if I define a function like this, first type, fx is equal to x for all x belonging to R. This is called what? Identity function. This is identity function, because x doesn't change, its identity remains as it is. Secondly, I can define f of x is equal to c for all x belonging to R. This is called constant function. Constant function, you take any real number, its outcome is c. Here what happens? Outcome changes according to x. If x is 2, f of 2 will be 2, f of 3 will be 3, f of 4 will be 4, f of 1 half will be 1 half. Here it is not so. F of x is equal to c. You take any x, outcome is constant. It is not changing. So this is a constant function. Then you know that functions like this, fx is equal to sin x, then cos x, then what? Tan x, etc. Sec x, cosec x, cot x, they are all trigonometric functions. This is a trigonometric function. Then you have functions called exponential functions. Fx is equal to e raised to x, or fx is equal to a raised to x. What are they called as? Exponential functions. Right? Then we have, say, polynomial function. Any expression of this type. Suppose I take f of x, and if it is written as a0 plus a1x plus a2x squared plus and so on, an x raised to n, where an is not equal to 0, then this is a polynomial function. This expression on the right hand side, a0 plus a1x plus a2x squared plus and so on up to an x raised to n, is a polynomial of degree n. So this function is a polynomial function. If you take only this one, a0 plus a1x plus a2x squared, it is a quadratic function, because maximum power is 2 and its coefficient is non-zero. So this is a quadratic function. So these are, generally we come across these functions. It is not the end of the list, but there can be many functions which we will come across. Logarithmic function is also there. So sixth function I can take, fx is equal to log x. And now each function for all here I can say, because the domain of the logarithmic function is all positive real numbers. So here for all x belonging to r plus, we will say. You cannot take log of negative real numbers. You cannot take log of 0 also. So log can be, log of some real number can be negative, but log of negative number or log of 0 is not possible. Log of 1 is 0. You take any base, log of 1 is 0, but log of 0 is not possible. So positive real numbers is the domain of this function. So all such ideas you must have. Every function when I take, what is the domain of that function? What is the codomain? What is the range of the function? All this study must be done properly. This is a high time to work on that. If I take sin x as the function, you know right from the 11th standard you have studied is sin x and also cos x. Their range is -1 to +1. You take any real number x, any angle you take, but sin and cos, they will be -1 less than or equal to sin x less than or equal to +1, or -1 less than or equal to cos x less than or equal to +1. So range of sin and cos function is minus closed interval -1 to +1. So this knowledge you must have. Whenever I study functions, I must have clear-cut idea of what is its domain, what is its codomain, what is its range, whether function is 1 1, whether function is onto, whether function is into, whether the function has an inverse. If it has inverse, what is the formula for the inverse? All such things you must study. You must develop this habit. Whenever any function you come across, immediately see what is the domain of the function, what is the range of the function, etc. Whether the function is 1 1 onto. All these things help you whenever we study sincerely the metric topology. All these ideas will be needed. That is why I am wasting one lecture on this. Actually it is not wasting. It is very important that we must come across all these things that we have already done in previous years mathematics. So this is all about basic theories of the functions. Now whenever I study analysis, I come across various types of the intervals. You have heard the words like open interval, closed interval, clopen intervals, etc. So what is it? Whenever I take say real numbers, suppose I take, this is closed interval. Whenever I say closed interval, the notation is closed interval AB. Obviously this is all done for a set of real numbers. Closed interval AB means what? It is the set of real numbers. Here it will be set of real numbers x belonging to R such that A is less than or equal to x, less than or equal to B. So both A and B are included, and all the real numbers between A and B are also in that set. Whenever I take open interval AB, it is x belonging to R such that A is less than x, less than B. Both the boundary points are not included in that set. All the real numbers between A and B, it is open interval. And there is a thing called clopen interval. So it is AB or it is open at A, closed at B. So in this set, A is included, B is not. So we will say x belonging to R such that A is less than or equal to x, less than B. And here this will be x belonging to R. Now here open at A, so A is not included, A is less than x, less than or equal to B. So these are 4 intervals we will come across: closed interval, open interval, clopen intervals. Clopen interval means closed open interval, or also it is termed as half open interval, because on this side it is open in case of this interval, and here on this side it is open. Open means that particular point is not included. Whenever both the boundary points and all the real numbers between those points are included, it is a closed interval. And when it is both the boundary points are not included, only real numbers between A and B, then it is open interval. So these are the ideas of the intervals, and we will use them many times in our study. Next thing is, we also require the knowledge of real numbers. As I told, real numbers are generally studied, and not only real numbers but many different sets we will study. And metric space, when you will study metric topology, actually when we will deal with, we are not only studying real numbers. It can be any non-empty set satisfying certain properties, but still real numbers has its importance. Real number, then R2, that means Euclidean space, R3, three-dimensional space, right? All those sets we will study, and in general also other many sets we will study. So, but does real numbers will have some importance, and you must know that set of real numbers when I study, what is it? It is actually union of rational numbers and then irrational numbers, R minus Q. R minus Q is set of irrational numbers. What is rational number? Right from the high school level you have studied that rational number is any number of the type P upon Q, where P and Q are integers and Q is not equal to 0. Such a number is a rational number. And whenever real number cannot be expressed in this form P upon Q, then it becomes an irrational number. Can you give examples of irrational numbers? Root 2, very simple. Root 2 is example of irrational number. Pi that we use, whose approximate value is 22/7, is an irrational number. E that we use is an irrational number. Root 7 is an irrational number. Root 5 is an irrational number. This doesn't mean the root of something is irrational. If I take root of 16, is it irrational number? No. Root of 16 is plus or 4 or minus 4. So it's an integer. Every integer is a rational number, we must know. So P upon Q, where P and Q are integers, and Q is not 0, because in mathematics division by 0 is never allowed. So if you write 2 upon 0, it's meaningless. It's not allowed also. 0 upon 2 is okay. You can divide 0 by any real number other than 0. But you cannot divide by 0. This is very important. So always whenever I am saying P upon Q, Q is not equal to 0. This is 100% fixed. Because nowhere in mathematics division by 0 is allowed. So any number of this type is a rational number, and whenever you cannot express number in this form, it becomes an irrational. So rationals and irrationals together form the set of real numbers. So whenever I study number theory, you always started with set of natural numbers, right? So it is always one sentence is there which tells that God created only natural numbers. Every other thing is a creation of human being. So it started all with natural numbers. Then we have whole number set. Whole number, which includes natural number set, union 0. Then we have integers, set of integers, all positive integers, negative integers, and 0 makes the set of integers. Then there is a set of rational numbers, and finally it is a set of real numbers. The hierarchy is like this. Natural number set is a proper subset of whole number set. It is proper subset of Z. It is proper subset of Q, and Q is proper subset of R. So R is the biggest set as far as real analysis is concerned. It goes beyond that because there is a concept of complex numbers, and R is subset of complex number because every real number is a complex number. Here what happens, every natural number is a whole number. Every whole number is integer. Every integer is a rational number. Converse is not true. If I take real rational number, it doesn't mean it is integer. Some rational numbers are integer. Every rational number is not integer. If I take 5, 5 is a rational number. 5 is integer also. But 5 upon 2 is a rational number. It's not integer. So Z is subset of Q. Q is subset of R. And further I can say that R is subset of complex number set of complex numbers. So every real number is a complex number. Every complex number is not real number. A complex number whose imaginary part is 0 is real number. I hope you remember every complex number means what? It is a number of the form a plus bi, where I is imaginary number. What is the value of I? Root of minus 1. Right? And whenever I write a complex number, it is written in this form a plus bi. This is called, suppose Z is this complex number, then what is the real part of Z? A. And what is imaginary part of Z? It is B. Both these are real numbers, but together a plus bi becomes a complex number. And whenever imaginary part is 0, this is 0, means it will be only A. And this is a real number. So every complex number is not a real number, remember. Every real number is a complex number, but conversely, it's not necessarily true. Some complex numbers may be real numbers. Which complex numbers are real numbers? Where imaginary part is 0. Those complex numbers are real numbers. Those real numbers are rational, because those real numbers which can be expressed in the form P upon Q are rational numbers. But there are many real numbers, root 2, root 3, root 7, e, pi, etc. They are not rational numbers. So the hierarchy is like this. Smallest set is set of natural numbers. It is subset of whole numbers, proper subset. Proper subset of set of integers, proper subset of set of rational numbers. It is proper subset of set of real numbers, and finally it is a proper subset of set of complex numbers. So this is the what we can say sequence of inclusion. This set is included in this set. This set is included in this set, like this. So this you must remember. If you take open set and closed set, because these are very simple ideas, but generally people don't give importance to these things, but these are very important ideas. Whenever I take open set, suppose I take open interval AB, and if I take closed interval AB, what is the relation between them? Which is subset of what? See here, whenever I say open interval AB, all the real numbers between A and B are included in this set. Whenever I take closed interval AB, A, B and all the real numbers between A and B are included. So naturally, open interval AB is subset of proper subset. See, in case of subset, sometimes this is written, sometimes this is written. What is the difference between them? This means equality is also possible. But here equality is never possible, because endpoints A and B are included in this set and endpoints are not included in this set. So this open interval is proper subset of closed interval. Open interval AB is proper subset of closed interval AB. Open interval AB is also proper subset of open interval AB. Right? But closed interval cannot be subset of this open interval. So this is the inclusions are very important. So knowledge of intervals, knowledge of the sets that we are going to use. Then which interval is subset of which interval, whether it is proper subset, whether equality is possible. All these ideas must be very clear, because the whole metric topology is built on these basic things. If you are very clear in your basic knowledge of set theory, then it is very, metric topology is very simple, you can easily understand it. So in this particular lecture, what I have tried to do is to explain the basic things that are needed in further development of study of metric topology. So we started with basic concepts of functions. What is domain, what is codomain, what is range, which types of relations are functions. Then we studied what is meant by a function is into, what is meant by function is onto, what is meant by function is 1-1. Then what is meant by function is bijective. How to check whether function is 1-1, how to check whether function is onto. Then how to calculate inverse of the function. And then the property that f of f inverse is original element. So if I consider f of f inverse x, I will get x again. And see, whenever I am taking f of g, it is called also as a composite function. We should know that. So in short, it is something like this. If I have a function f from a to b and another function g from b to c. So if I take x belonging to a, you know my f of x will be in b. Now domain of g is b, so I can operate the function g on fx, because fx is element of b. I can operate the function g on the domain of that function. Domain is b, this is also element of the domain, so I can think of g of fx. This is called as a composite function and written as g circle f of x. So g circle f, this is also a function, and it is function from a to c. Because why? G of fx I am calculating. Fx is from b and g is a function from b to c. So whenever I operate the function on the elements of b, I get element of c. This fx is element of b, I am operating the function on that element, so I will get function or element of c. So whenever I have a function f from a to b and g from b to c, I can think of g circle f and it will be a function from a to c. This is called composite function. Right? Now g circle f is possible. Is f circle g possible? Can you answer? F circle G, is this function possible? F circle G means what? I am operating f on gx. Now G is a function from B to C. So Gx will be from C, and F you cannot operate on the elements of C, because domain of F is a function you can operate only on the elements of the domain. Here domain of G is G of x. Whenever I am checking, G of x belongs to C, and C is not the domain of the function f, because domain of the function f is A. So G of fx is not possible. So in mathematics, you know that whenever in case of addition, when you say a plus b, in case of real numbers, a plus b is same as b plus a. What is that property called? Commutative property. Same thing here. Here you have calculated G circle f, but f circle G is not possible. This function does not exist itself. So what I will say, composition of the function is not commutative. F circle G need not be equal to G circle f. Now if you have functions like this, see, suppose I have a function, one function say f from R to R. See, f is a function from R to R, and another function G from R to R. Now it is no problem, because here everything is R to R. So here f circle G and G circle f both exist. But are they equal? The question is whether f circle G is equal to G circle f. Now how you will check whether two functions are equal? Simple rule is, I will operate that function on fixed element, and if the output is same, then the functions are equal. See, suppose I take one simple example I will take. F is a function from R to R you take, where you take f of x is equal to say x square for all x belonging to R, and another function you take, f is a function, say G is a function from R to R, and say G of x is equal to say x plus 2 for all x belonging to R. Now what is f circle G of x here? It is f of gx. What is gx? X plus 2. So it will be f of x plus 2. Now what is fx? X square. So what is f of x plus 2? It is x plus 2 bracket square. It means it is x square plus 4x plus 4. What is G circle f of x? You know, it is G of fx. What is fx? X square. So it is G of x square. And what is G of x? X plus 2. So it will be x squared plus 2. So if I take this as 1, this as 2, you can easily verify that x square plus 4x plus 4 is not equal to x square plus 2. And so f circle G, G circle f both exist, but they are not equal. So composition of the function is not at all commutative. First thing is, it may not exist also. It may happen that f circle G exists, but G circle f does not exist. In some cases, in functions like this, both f circle G and G circle f exist, but they are not equal, because whenever I operate f circle G on x, my output is x square plus 4x plus 4, and whenever I operate G circle f on x, my output is x square plus 2. Definitely they are not equal. And so composition of the two functions need not be commutative. In some cases it may happen, luckily, that f circle G of x is same as G circle f of x, but in general they are not equal. So this is the idea of composite of the functions, and composition of the function only is possible whenever case like this, f is a function from A to B, so codomain of the first function is the domain of the second function, then G circle f is possible. See here, codomain of f is domain of G, so G circle f is possible, but f circle G is not possible. So composition of the function, this is called composite functions, f circle G. So this notation circle is used as a composition of the two functions. This is not commutative. So this is the thing that we wanted to discuss in the first lecture. This is very basic lecture where I gave you idea about the functions, the various types of the intervals and composite functions. In next lecture we will start with actual metric topology, and in that study we will need all these basic ideas about the functions, and also in the next lecture we will actually discuss what is metric space and some examples we will consider of the metric space. Thank you.